Hello everybody, and welcome back to an engineering statics midterm example. In this midterm example, we're going to be covering a very old midterm, the 2012 midterm, and more specifically, we're going to be covering question number 2. Now, question number 2 is focused on moments. So if you guys want something to do with moments, this is your question. If you guys don't care about moments, well, this may not be the video for you guys. But most of you guys are probably interested in moments, so let's jump into this question. Before we begin, as always, doesn't matter if it's an example or a lecture video, I hope you guys are doing well. Make sure you guys take time for yourselves. You are the number one priority you should have. Always. It doesn't matter how busy school gets, how busy work gets, you're always the number one priority. At least to me, you're my number one priority, so I hope you guys are doing well. Alright, now that that's out of the way, let's jump into the fun. So this is actually not too bad of an example, but it emphasizes something that I find most students have a lot of trouble kind of comprehending, or not even comprehending, but just trouble in general. So we're going to cover it. So the question itself says, as shown in figure 2, which is the only figure that you guys are going to see, the weight of the triangular prism is W and is located at point G. So basically the center of mass is at point G. It says a force F of 200 kilonewtons is applied at point D and is directed along the line DH. So I'm just going to switch over to my pen, and it's basically referring to this force right here that we are now going to have in red, just to make it pop a little bit more. As we can see, the force starts at D and it goes over to point H. Now, the question wants us to do three different things. The first one is find the force F and express it in Cartesian vector notation. Well, that's not too bad. Part B says determine the magnitude of the moment of F along line AB. So this is going to be a little bit different than what we're used to. Remember, when we do cross product, we're finding the moment about a point. We're not finding the moment about a line, we're finding the moment about a point. So for part B, we're going to start with cross product, but we need to modify it a little bit more to actually create a moment about a line. And then finally, part C says, determine the weight W so that the resultant moment of F and W about line AB is 0. Basically, what this question is asking is, pretend that this line right here, AB, which I'm going to highlight in kind of an orangey color, pretend that was a door hinge. If I put that force F of 200 kilonewtons, we know that it wants to rotate my door upwards. But we know that the door has a weight going downwards, so it's basically saying, what is F and W so that the door does not rotate at all about that line? That's all we're trying to find, is what is the forces that will basically create equilibrium. Now that's going to scare some students. Please don't get scared. Don't run away. This is not an equilibrium question. It's simply a moment question, because we know that the two moments in this case are going to be equal to each other. So I'm just going to erase this, and we are going to start off with part A. So it says find the force F in Cartesian vector notation. Right now we are given F as simply a magnitude. And if you guys go back to the theory videos, I said that there's three different cases that we have to get a 3D force into Cartesian vector notation. The first is a trigonometry case, which we are not really given any angles, so that doesn't apply. The second one is coordinate direction angles, which we're not given, so we know that doesn't apply. And then the final one is a position vector case. And this is the case when we are given 2 points along the line of action of our force. And if we look at this question, we are given point H and we are given point D. So since we are given coordinate points, that should be kind of the first major red flag that, hey, we are dealing with position vectors. So I'm going to scroll down a little bit here. Hopefully it's not too bad. I'm going to switch it to red. And we are going to go part A. And again, the whole goal here is to get that force F into Cartesian vector notation. Now, the process for the position vector case is actually relatively simple. We are going to find a position vector between the 2 points. We are going to normalize it by basically dividing by the magnitude to get the unit vector. And then we are going to multiply the magnitude of F by that unit vector. That's all we're going to do. So the first thing that we are going to do is we are going to create a position vector. So I'm going to go R. And it's going to go from where our force starts to where our force is going to. So in this case, we can see that our force starts at point D, and we know that our force is heading to point H. All right, so that's going to be the subscripts, where we start to where we end up. Now, we calculate this specifically by taking the point where we end up and we subtract it from where we started. If I want to find the relative distance something is moving, I'm going to go from where I end up, my final position, minus where I started, my initial position. So in this case, if I start at point D and go to point H, I'm going to take my final position H and I'm going to subtract where I started, in this case, D. So from there, it's actually pretty simple. All we need to do is take our coordinate points. So for H, we're given as 0, 0, and 9. And I'm going to subtract that from D, which we have as 9, 9, negative 6. So if I do the math here, it's actually not too bad. I'm going to scroll down a little bit so that my hand doesn't fall off the side of the iPad. We are going to get a vector of 0 minus 9, so we're going to have negative 9 in the I direction, 0 minus 9, so negative 9 in the J direction, and then finally 9 minus negative 6, so we know that this is going to be plus 15 in the K direction, just like this. And it's a position vector, so it's going to have units of distance. In this case, all of our coordinate points were in meters, so we know that this is going to have units of meters. All right, so not too bad so far. And again, before we can actually start multiplying this into our force vector, we have to normalize it. Basically, we have to find the unit vector. Now, the unit vector is easy because all we're going to do is take those three components that we determined, negative 9, and 15, and we're going to divide them by the magnitude of this position vector. So I'm going to say, okay, I now know the position vector, so if I want to, I can find the magnitude of RDH, and that is simply going to be the square root of all the components squared. So I'm going to make a little square root sign. Component 1, negative 9 squared, plus component 2, also negative 9 squared. Finally, plus component 3, which is 15 squared. Now, if you guys don't want to, you guys don't have to write the negative sign. We all know that a negative squared is just going to turn into a positive, so it doesn't really matter too much. I just want to avoid as much confusion as possible. I know there will always be that one kid that's, Clayton, how come you put 9 instead of negative 9? Well, it doesn't matter, but I really want to eliminate that confusion. Now, if you guys were to take all this, throw it into your calculator, you get 19.67, and it's going to have units of distance, so this is going to be meters. Now, Clayton, what does this physically represent? Well, it means that the distance, and I'll go over to, let's say, blue, the distance between these 2 points, that physical distance, this right here is 19.67 meters. That's what the magnitude of a position vector represents. So now that I have my position vector and I have the magnitude of my position vector, I can find the unit vector dH by just taking all those components and dividing by this 19.67. So I can say my unit vector dH is going to be equal to, and I'm just going to put in brackets here, and I'm just going to go through all those components and divide by 19.67. So my first component was negative 9, so I'm going to take negative 9, and then I'm going to divide it by 19.67, and this will be in the I direction. The second component was also negative 9, so we're going to have negative 9 divided by 19.67 in the J direction. And then finally, our last component was positive 15, so we're going to say plus 15 divided by 19.67, and this will be in the K direction. So you guys can do the math to actually find out these numbers, but I just tend to leave it like this. It doesn't make a big difference. The one thing that you're going to want to keep in mind is that the units of a unit vector, well, there are none, okay? So don't put any units. And the reason why is actually kind of simple. I'm going to switch over to pink. Our top component, let's say for the I direction, was negative 9. So we know that this is negative 9 meters. We're dividing it by the distance. So our distance at the bottom is also meters. So what ends up happening is that they just cancel out like that. That's why it doesn't have any units. So I'll get rid of that. So now that we have this unit vector, we can find our force vector by simply taking the magnitude of our force and multiplying it by each one of the components. So for the I component, I'm just going to multiply by 200. For the j component, I'm going to multiply by 200. Again, 200 is the magnitude of our force. That's why I'm multiplying by 200. So I'm going to come down here. This one will also be multiplied by 200. And once you do all of the math, which is pretty simple, you will find that your force vector dH is going to be equal to, and then I do the nice squiggle brackets, it's going to be negative 91.5 in the I direction, negative 91.5 in the j direction, and then finally it's going to be plus 152.5 in the k direction. So not too bad at all. And it's going to have units of force, and in this case we have units of kilonewtons. So that's going to be part A. As we can see, when I explain everything, it takes a while, but realistically, you guys are all so fast. You guys are going to fly through this question. It won't be too bad. So that's going to be part A. Now, if we look at part B, it says determine the magnitude of the moment F about the line AB. So I'm going to erase a couple things because we don't want to confuse ourselves. Erase this. So basically, we now know what F is in Cartesian vector notation. So we now know what F is. I'm going to put a little check mark there. Now the question says we now have a line AB. So I'm going to highlight it in pink. A line AB. And what the question wants is the magnitude of the moment created about this line. Now when you're dealing with moments about a line, okay, about a line, not about a point, but about a line. The trick is to find the moment about a point on that line, and then we use dot product. Whoa, Clayton, that sounds like a lot of steps. Well, it's not too bad. The first step is going to be we need to find the moment F creates about any point on that line. It doesn't matter which point, just any point. So in this case, I'm going to look down and say, okay, this line has 2 points. I'm going to switch to blue so we can really see them. It has point A over here, but it also has point B over here. So it doesn't matter which one you guys take. What I'm going to do is I'm going to take the moment about point A. So I'm going to take the moment about point A. And you guys are saying, okay, well, that's not too bad, Clayton, but how do we take the moment about a point? Well, we do cross product. So the moment, and I'll write this up here, and then we'll write it again down there. The moment about A in a vector form is going to be a position vector cross with our force vector. So it's going to be cross with our force vector, and our force vector was dH. So okay, that's not too bad. But what is that position vector? So what is this? Oh, I just about erased it. What is this position vector right here? Well, this position vector goes from the point we want the moment about to anywhere on our force vector. Okay, I'm going to repeat that again. It's going to start at the point we want the moment about, in this case point A, and it can go to anywhere along the line of action of our force vector. So let's switch colors, let's do it in green. So for instance, we know that we are going to start at A, and we can go to any point along the line of action. So if I want to, I could go from A over to H. That's perfectly valid. Another option that I have is I can go from A over to D, because D is also along the line of action of our force vector. Again, that's perfectly valid. If we had a third point, let's say that we had a point right there, kind of in the middle between D and H. If I wanted to, I could have a position vector that goes like this. Cross product, it doesn't matter. You're going to get the same answer no matter which position vector you take. So I'm going to erase kind of the ones that I don't use. And what I'm going to do is I'm going to use the position vector from A to D. So in my little equation up here, I'll erase the highlighting. I'm going from A to D. Again, I'm starting where I want my moment about. In this case, it's point A. And I'm going to my force vector. In that case, it's going to be point D. So let's go down here and say, okay, for part B, and I'll switch back to red. I'll come down here, we'll go B. I said, okay, my moment about point A is going to be a position vector from A to D cross with my force vector AD. Now, if I look at this equation, it's simple. I can calculate my moment if I know two things, the position vector and the force vector. From part A, we already know what the force vector is. I'll switch to pink. We know that this force vector is just right above. And I set A to D. We actually know that this is DH. DH. So we already have that. That's good to go. The only thing we don't know is the position vector. But again, position vectors are easy because we know that a position vector from A to D, it's just going to be equal to the coordinates of D subtracted from, or I guess the other way around, minus the coordinates of A. Nice and simple. So what we're going to do is we're going to say, okay, position vector, or sorry, coordinate point D, as we can see down here, is 9, 9, negative 6. So I'm going to come down here and say, okay, we got 9, 9, negative 6. And we are going to subtract the coordinates of A. So if we scroll up here, A, which is kind of already highlighted in blue, it's 9, 9, 0. So I come down here, we say we subtract 9, or I guess 0, 0. I make so many of these little mistakes. I must be a little bit dyslexic. I always get these numbers and letters mixed up. All right, so once we do all the math here, it's actually pretty simple. We can see that our position vector is going to be 9 minus 9, so this is 0 in the I direction. 9 minus 0, so negative 9 in the J direction. And then finally, negative 6 minus 0, so it's going to be negative 6 in the K direction. Just like that. It's a position vector, so it's going to have units of distance, in this case, meters. All right, so now we're looking pretty good, pretty sexy. The next thing that we need is to cross them together, because now if we look at our cross product formula, we have the position vector, we have our force vector, we are technically good to go. So what I'm going to do is I'm going to scroll down a little bit because the page is kind of ending. I'm going to say, okay, this cross product, so the moment about A is equal to, and I'm going to put kind of my cross product things. Remember, cross product is going to have basically 3 rows. The first row is always going to be that IJK. IJK. Doesn't matter what you're doing, unless it's triple scalar product, but you guys shouldn't be doing that. It doesn't matter what you're doing, this is what you guys are going to do. And then the second row is always going to be the components of the position vector, all right, the position vector. So if we look at our position vector, which is still on screen above, we see that it is 0, negative 9, negative 6. Not too bad. Actually, it should be positive 9, not negative 9. See, just saved myself a lot of time right there. All right, moving down, the last row is going to be the components of our force vector. So I'm going to scroll up. Right there, we can see that the components of our force vector are negative 91.5 for I and J, and then 152.5 for K. So I'm just going to scroll down, so save myself some room. Negative 91.5, negative 91.5, and 152.5. Looks a little bit wonky. I didn't really write it out as nice as I should have. Let's fix that really quick. You guys deserve the best. You guys don't deserve some wonky stuff. So let's go 9, negative 6. This is going to be J, and this is going to be K. So how do we do the cross product? Well, as you guys have seen from your instructors, there's many ways of doing the cross product. I do the fish method. I know that some of you guys seem to like the fish method, which is great. If you don't like it, that's perfectly fine. The best method to do something is the method that you guys find the easiest. That's all that matters to me. If you guys have a method that you find is simpler, please do it. I want you guys to be as happy as possible. So what we're going to do is we're going to do the fish method because that's what I prefer. And it's pretty simple. We know that we have a moment vector. So I'm going to circle this really quick, a vector. The key for a vector is that we are going to have 3 components. Okay, guys, we have 3 components. So what I'm going to do to find each component, I'm just going to erase this line real quick, is I'm going to cross out the column of the component I'm interested in and then draw a fish. Sounds pretty simple, right? Well, what do you mean by that? Well, if I'm interested in the I component, I'm going to draw kind of a and basically cancel out everything in that column. The components that are left, I'm going to draw a fish. So I'm going to go 9 to 152.5, up to -6, and then down to -91.5. And I'll keep it in blue so that we can see where everything is coming from. So I can say, okay, this vector is going to be equal to, and then I'm just going to basically trace the line of the fish. We go from 9 down to 152.5. So I'm going to go 9 times 152.5. And then once we go around the fish, we go minus, and then we go from -6 down to -91.5. So -6 times -91.5, just like this. And that, ladies and gentlemen, is going to be our I component. We just got to throw it all into our calculator, and we'll do that a little bit later. So now I'm going to erase all this and say, okay, that's the I component, but I also want a J component. So I'm just going to switch back to the dashed line. If I want the J component, I'm going to draw a dash through the J column, more or less. And then I'm going to draw my fish yet again. So I'm going to go from 0 to 152.5, up to -6, and down to -91.5. I'll go back to normal and say, okay, we know, I'm just going to scroll down, that this is going to be, again, just the path of the fish. We go from 0 to 152.5. So I'm going to say, okay, 0, 152.5, subtracted from -6, multiplied by -91.5. So -6, -91.5. What's nice about the fish method is once you guys get it for a couple times, it actually becomes pretty simple. You don't need to draw a fish at all. It's quite a nice pattern. So again, this is going to be the J component. But there's one thing you have to keep in mind. There's one trick to the fish method, one trick, and that is this. At the beginning of our J component, we have to have a negative sign. That's going to be subtracted from everything that we just calculated. That's going to be the J component. For the K component, it's the exact same thing. I draw a dashed line. I'm not going to do it. I think you guys know exactly how it goes by now. So we are just going to calculate it normally. So I'm just going to put a bracket. For the K component, it is going to be 0 times -91.5 minus 9 times -91.5. So this right here will be for our K component. This will be the end of the vector. And the K component starts off with a positive. It's only that J component that actually starts off with a negative. And since we have moment, it's going to have units of kilonewtons times meter, basically force times distance. Once you do all the math, and I know it looks pretty gross, you will find that our moment, oops, sorry about that, our moment about point A is going to be equal to, and I'll just take a look at my notes, 823.5 in the I direction, 549 plus 549.0 in the J direction, and then finally plus 823.5 in the K direction. Again, units are going to be kilonewtons times meters. So that's my very long process of showing you guys the cross product. Again, I'm looking at the time. This is a 25-minute video already. You guys can do this much quicker because you guys know exactly what to do. You don't need to go through all the steps that I'm explaining in excruciating detail. I know I'm probably putting half of you guys to sleep. I'm sorry about that, but I want to make sure you guys know every one of the steps. So we're going to come up to the top here, and we are going to say, okay, I'm going to erase a couple things so we can start talking about what we have. Don't need this. I'll go back to pink. Remember, we wanted the moment about this line AB. And at this point right now, we now know the moment at A. We know the moment at A. So we basically have the moment vector. But now what we want to do is we want to find the component of this moment vector along that specific line. How do we find a component of something along an arbitrary axis? Well, it's going to be dot product, okay? Dot product. So moment about a line, in this case AB, is going to be equal to our moment dotted, I guess our moment about A, I'll be specific, dotted with the direction of that line. So we know it's going to be dotted with the direction of the line. As we remember, directions are defined by unit vectors, and it says specifically in the question, it wants line AB. So we know that a unit vector has to go from A to B. So that's the trick. Once we have all these components, we dot them together and we have our magnitude. And it's not too bad, because if we look at this formula, I'll switch to blue, we now know the moment about A, so we can put a little check mark. The only thing that we don't know is that unit vector AB. But one thing that we do know, which is nice, is we know the coordinates of A and we know the coordinates of B. If I know the coordinates of 2 points, I can find a position vector between them. And if I have the position vector, well, then I can find the unit vector. So it's all coming together. Isn't that nice? So we're going to come down here and say, okay, I have my moment, but the last thing that I need is the unit vector AB. And I start off by finding the position vector AB. So if I want the position vector AB, it's going to be the coordinates of B subtracted from the coordinates of A. So this is going to be equal to, I'm just going to scroll up. Coordinates of B are 0, 12, and 0. So I'm going to come down. I'm going to input them, 0, 12, and 0. And I'm going to subtract the coordinates of A, where I start from. So I'm going to come up. Coordinates of A, as we can see, are 9, 0, and 0. So I'm going to come down. We're going to have 9, 0, 0. And what you guys will find is that the position vector is pretty simple. It's going to be negative 9 in the I direction, plus 12 in the J direction, plus 0 in the K direction. We'll end our squiggle brackets, and this, of course, will have units of meters. Now, in order to find the actual unit vector, we have to take our position vector and divide it by the magnitude. So the next thing I need to do is say, okay, I have RAB. If I want the magnitude of RAB, all it's going to be is the square root of all the components squared. So I'm going to have negative 9 squared plus 12 squared plus technically 0 squared. Again, you guys don't need to put that kind of stuff, but I want to include it because there will always be that one troll in the comments that makes a comment about it. All right, so once you guys do all the math, you guys will find that this is equal to exactly 15 meters. So if I now want the position vector, AB, UAB, all it's going to be is each component divided by 15. So I'll put my squiggle brackets. We have negative 9 over 15 in the I direction. We have plus 12 over 15 in the J. And then we end off with, of course, plus 0K. 0 divided by 15 is still 0, so we don't need to really worry about it. So now we have everything that we need. All that's left is just to dot the two things together. So I'm going to come up, or I guess not come up, I'm going to scroll up a little bit. I want to keep the moment in the frame. Wow, it just goes to show how crooked all my writing is. Again, for those of you who don't know, I write sideways, which is kind of funny. Well, maybe funny. You guys might just say, well, it's just kind of dumb, Clayton. All right, so our moment, AB, is just going to be the dot product of our moment vector, A, which we have, dotted with the unit vector, AB. So all we're going to do is take the components and multiply them together and add them. So my first component, actually I'll switch to pink, is we're going to take the I component, negative 9 over 15, and we are going to multiply it by 823.5. And I'll keep it like this so that we can see. So we got the 823.5, and we're now multiplying that by negative 9 over 15. That's our first component. And I'll switch to blue. Our second component, so we're going to go plus. The j, we have 549.0. I'm just going to scroll up a little bit. Don't worry, I'll go back. 549.0 multiplied by the second j component, 12 over 5, or I guess 15. And then our final component, I'm not going to worry about it too much because as we can see, the k component of the unit vector is 0. So technically we have plus 0. Once you guys do all the math, because again, we're not really getting a vector, you will find that the moment about AB is going to be equal to negative 54.9 kilonewton meters. Now here's the trick, and this is actually a very important trick for those of you who are doing this online. If we look back up at the question, all the way at the top, it says determine the magnitude. The magnitude. It doesn't want a direction associated with it, it just wants the magnitude. So if this was the actual question, even though the moment is negative 55.4, which basically means it's going clockwise, when I enter this, our moment, AB, or more specifically, I guess our magnitude, is going to be equal to 54.9 kilonewton meters. Why is this important? Well, if I was marking a physical exam, I can see what you guys did, so I can say, okay, they did 9 out of 10 steps correctly, I can give them 90%. But if this was an online exam where you're just entering numbers in, if you enter negative 54.9, well, the computer is probably just going to give you 0. So it's very important that we read these types of questions. That's going to be part B. Again, it's pretty long because we have cross product. Now, the last part says determine the weight W so that the resultant moment of F and W about line AB is 0. So if we look at this particular case, I'm going to erase everything so that we can kind of have a good indication of what's going on. There we go. We are now concerned with this force, and I'll put this force in purple. We have a W force going downwards. Now it's pretty easy to see that when we have weight, I'll come over to the side here. Actually, I'll erase all this too. Just make it really simple so that we're not getting things mixed up. So when we have a weight force, we know that it's just purely going downwards. So my vector would be something like 0i plus 0j minus w in the k direction. And this would be kilonewtons. The problem that we have here is we don't know what that W is. The whole goal of this question is to determine W. And it even says it. Determine the weight W. The thing that we do know is that the moment W creates about line AB is going to be equal to the same moment that we derived right here. We know that that moment, let's see what, yeah, I'm still in pink. We know that our moment must be equal to the 54.9. So what we're going to do is say, okay, we're going to look at what relationships we have. So if we come up here, if I want to determine the moment about that W creates about a line, remember we said the first step that we have to do is find the moment about a point. So I'm going to do the same procedure before. I'm going to pick point A over here, and I'm going to find the moment W creates along point A. Now this is why I kind of hinted at the very beginning of the video that there's a special trick, and that is this. This is what usually gets students in cross product. Cross product, students are very used to moving forward. I have position, I have force, I can find a moment. Now it's a little bit tricky because that one component of our cross product, in this case force, we don't know what it is. So this is my kind of pro gamer tip to you guys. If there's an unknown component on the left side of the cross product, just keep it as a variable and conduct the cross product like you normally would. So if we look at our W vector, which is kind of over here, we don't know that k component. But don't freak out. All we're going to do is we are going to just pretend that we do know it. Let's just pretend it's W, and we are going to carry on throughout everything else. So I could say, okay, if I pretend that I know what my W force is, all I need to do to find the moment is cross it with a position vector that starts at my point A and goes to a point on our line of action of our force. Now, the line of action of our force, we only are given one single point that it crosses, so we are going to pick point G. So I'm going to come down here. I'm going to say, okay, we are now dealing with part C. And we know that the moment about A, and this one's due to the weight, is going to be a position vector, AG, goes from point A to G, cross with our weight vector. So we're going to do the exact same thing before, where the first thing that we need to figure out is what is this position vector AG? Well, we know it's going to be equal to the coordinates of G subtracted from the coordinates of A, which is going to be equal to, and if I just scroll up here, it's pretty easy to see, G, I guess it's a little bit hard to see, is 4.59 comma negative 4. So come down here, 4.59 negative 4 subtracted from the coordinates of A, which if I scroll up is 900. I don't know why I always say 900. It's probably that guy in the midterm review session that kept saying 9, like the German word 9. I'm not too sure why he did it, but I got it stuck in my head now. So if you know him, or if you are him, congratulations. You've impacted me. All right, so when you do all the math here, it's not too bad. 4.5 minus 9 is going to be the negative 4.5. So I guess we have negative 4.5 in the I direction. And we have plus 9 in the J direction. And then finally we have negative 4 in the K direction. Just like that. And we get that this is going to be units of, not kilonewtons, I'm an idiot. It's going to be units of meters, units of distance. So now that I have that position vector, it's very easy to go and determine the cross product. So I'm going to come down here. We're going to do the same thing as before, where our moment about A, I'm going to draw that nice big line. We're going to start off with our position vector because it's the longest. We have our components negative 4.5, we have positive 9, and we have negative 4. Our force vector we know was 0, 0, negative W, and then our components at the top were I, J, and K. So it's going to look something like that. And then all we have to do is basically whatever method you prefer. So I'm not going to tell you guys which method you should use. Again, I think that's completely up to you guys to decide, hey, I prefer cross product, or sorry, I prefer the fish method. I prefer, I don't know, Dr. Cruz's method, whatever you guys want. So I'm just going to do it really quick because again, I've already explained cross product in excruciating detail. We don't need to do it again. So we have 9 times negative W minus 0. That'd be in the I direction. We have minus, because remember J always starts with the minus sign, negative 4.5 times negative W. And then we have minus 0. That's in the J direction. And then finally we have 0 in the K direction. So this is going to be our moment. As we can see, I'm just going to write it out like this. So it's going to be negative 9W in the I direction. We got positive, then it's negative 4.5 W in the J direction, plus 0 in the K direction. Now, of course, it's moments. It's going to have units of kilonewtons times meter. And that's what we do. So remember, we didn't know what W is, and that's what usually scares off a lot of students. What did I do? I just left W as a variable, and I carried on through like I knew what it was. So again, this is our moment about A. So I'm just going to write that down because that's important. Now that we have it about A, and I want to find it along the line, we are going to do the same process that we did before. So I'll just switch over to orange. We're going to do this. Our moment about a line is going to be our moment about that point dotted with the unit vector of the line. What's nice for us is we've already solved for the unit vector of the line. Again, looking at orange, it's going to be this one up here. So we have it. All we need to do is just do our same steps as before. So the moment about AB is going to be equal to our moment at A that we have above, dotted with the unit vector AB. So this is just going to be equal to the I component of our moment, which we had as negative 9 times W, dotted with the unit vector I component, which we have as negative 9 over 15. So negative 9 over 15 plus our second component, or our J component, we have negative 4.5 W multiplied by the J component above, which was 12 over 15. So plus 12 over 15. And we said that the K component is equal to 0, so we're just going to put a 0 at the end there. So what we end up getting is that our moment is equal to 1.8 times W. Now here's the trick. The moment line AB is equal to 1.8 W, and we said that we want this equal to the moment about the other force, which we had as 54.9. So if I were to look at just this equation right here, this equation by itself, our only unknown is going to be W. So I can solve for W, and I see that W, of course, is equal to 30, I was going to say 35, but it's not. It's 30.5 kilonewtons. And that's it. That's all. That's how we solve for W. The trick to part C, and this applies to a lot of different things that I'm going to mention, is that we have the cross product, but we don't know one of the components of the cross product. In this case, we didn't know the force vector. If you guys are ever in a situation where you do not know the components of one of the cross products, just keep them as parametric. Keep them as alpha, keep them as W, whatever, and always try and just move through the cross product. That's typically the case when the question gives you a moment and wants a force, or it wants a position, or we have to work backwards. We don't try to divide the cross product, anything like that. It doesn't really work that way. We always have to move forward. So again, the key trick here, and I'll just highlight it one more time in blue, is we just set the unknown as a parameter and we just carry on through. So that's it for question number 2 of the 2012 midterm. Long video, but again, I over-explained it. Chances are you guys could probably finish this in 20 or so minutes, which should be a good time. Hopefully it's all clear now. There's no questions or miscommunication or anything like that. So yeah, that's it for this video. Thank you guys so much for watching. I really appreciate it. I will see you guys in the next midterm example.